Okay, good afternoon.
1/8
Naririnig po?
arcan ng
Yes po, ma'am. Yes po, ma'am.
Okay, good.
So, ang A
Okay,
natin ay
so for today, we will
dahil
have the shaft design, okay? So when we say shaft design, okay, a shaft is simply a rotating member which transmits power, okay? So there are different samples of the shaft. Meron po tayong tinatawag na line shaft, okay? Meron din po na main power transmitting shaft, and also those what we call the spindles, okay? Yung spindles po, ito po yung maliliit na shafts which we use doon po sa atin mga toy cars, okay? If you are familiar with a dynamo, okay? So the rotating member in a dynamo, you call that the spindle. So it's a short shaft or a small shaft, okay? And then when we say secondary or counter shaft, it is simply main function of the shaft is to transmit power, okay? But then if it is used only to provide rotation to the other shaft, that would mean a counter shaft, okay, or a secondary shaft. But the one which really drives the machine, okay, and transmits power, you call that the main power transmitting shaft, okay? So those are the classifications. Now, how do we design the shaft, okay? So to design the shaft, we have there two bases, okay? So the first one, that is based on loading, okay? So we are to look at the forces acting on the shaft. And from those forces present in the shaft, okay, that would be the basis of our design, okay? So based on the loading, we have therefore the first one, if the shaft is under pure torsion, okay? So the only load that we have on a shaft is the torsion, okay? The second one, you have their pure bending, okay? So even the shaft can be subjected to a bending load, okay? The third one, you have their combined loadings, okay? So pag sinabi po natin na combined loading, it would be a combination of torsion and bending, okay? And then the last one, we call it the variable combined, okay? When we say variable combined, still it is torsion and bending that is being combined. The word variable here would mean the torsion is varying. Same thing with the bending load. Okay, that is why it is called a variable combined loading. Okay, so this would be the basis, okay, of designing your shaft. This would be the basis of determining the dimension of your shaft, okay? So based on the loading. The second one, okay, we can base design on code. Okay, when we say code, these are detailed procedures, okay? Detailed procedures on how you will be designing for a specific shaft, okay? So based on the code, we have there, the first one is called the ASME code. And then the second one is the PSME code. Okay, ASME is American Society of Mechanical Engineers. PSME is Philippine Society of Mechanical Engineers. Okay, so these two, they devise a procedure on how you would design for the shaft. Okay, so they, in terms of the scope, ASME is known worldwide. Okay, so this is more on a standard method. Okay, this is more on a standard procedure. Yung ASME, okay? But then when we say PSME, okay, this would be good only on the Philippine setting, okay? So it is only on the Philippines that makes use of this code in designing the shaft, okay? So these are the two bases on how you determine the dimension of the shaft. So when we say shaft, this would be more on a circular cross-section, okay? It's either lang po, we have a solid or a hollow one, okay? So this is what we are designing, okay? What would be the diameter of the shaft to be used? Okay, considering the loads, considering the code. Okay, so when we say it's hollow, then you have to determine two dimensions, okay? The inside and the outside diameters, okay? So these are the basis on how we will be designing our shaft, okay? So how do we compare the two bases, okay? If you are to compare the two bases, based on code would be easier, okay? Why? It is because it has a detailed procedure on which you will simply follow or adhere, okay? That is why that makes it more easier to use than that of based on loading, okay? So this would be the first part of our discussion, okay? Let us have first the shaft design based on the loading, okay? The first two, pure torsion and pure bending, this is just the same as our topics in before the midterm, okay? Simple stresses to be specific, okay? This is machine members under pure torsion, okay? This one would be machine member under pure bending, okay? So those basically are the procedures on how you will be designing the shaft, okay? We are only restricted to only one kind, a circular cross-section with a solid or a hollow configuration, okay? Not unlike that of bending that we have on our midterms, okay? There we consider different cross-sections. We have the regular cross-sections and the irregular cross-sections, okay? So this time, bending is focused on shaft only, okay? So a circular cross-section, solid or hollow configurations, right? So let us start with this, okay? Shaft design based on pure torsion, okay? So a shaft design under pure torsion. Okay? So what you see here is the schematic diagram of the shaft, okay? So this long straight member, this is your shaft. And notice that on two ends, okay, you have there the square cross section and they have their square with an X, okay? So this refers to the bearings, okay? So it refers to the bearings, okay? And this is mainly your shaft, okay? So you have here the two bearings. Now, when you say shaft under pure torsion, you have here the rotation, okay? So this refers to the torsion of the member, okay? So how do we design this member, okay? So we call the induced stress, okay? So we call the induced stress simply as the torsional shear stress. And recalling equation for tau for torsional shear stress, general equation is tau equal to Tc over J. Okay? T pertains to the torque, okay? C is a radial distance, and J is the polar moment of inertia. Okay? And as applied to a solid shaft, yan po yung na-derive natin dati. Okay? If it is solid, okay, tau for solid would be equal to 16T over pi dq. Okay? If you could recall. Okay? Coming from this Tc over J, we come up with tau for solid equal to 16T over pi dq. And tau for hollow would be 16TD over pi quantity d to the fourth minus d to the fourth. The big letter D here pertains to the outside diameter, and the small letter d pertains to the inside diameter. Okay, so this is the induced stresses, okay, for shaft under pure torsion. As I have said, this is just the same as members under pure torsion. Okay, we incorporate solid and hollow shaft. Now, we will be introducing here now what we call diameter ratio. Okay? So we are to introduce this diameter ratio. For diameter ratio, we use symbol K. Okay? So K is equal to D over D. That would be inside over outside diameter. That will give us the diameter ratio. K equal to D over D. So don't get confused with the K na ginamit natin, okay, on other topics. We have on other topics, we make use of K also for the least radius of gyration. That is on our, I think, compression member, okay? But then here, the K value refers to diameter ratio, which is the ratio of the inside over the outside diameter, okay? So let us consider this on our solution, okay? Let us introduce this diameter ratio in our solution, okay? So let us recall this two, okay? So for the hollow, let us have that equation for the hollow shaft. For the hollow shaft, this is 16 kd over pi quantity d to the fourth minus d to the fourth. Okay? So, to introduce the diameter ratio, the denominator is to be multiplied by d to the fourth over d to the fourth. Okay? You look at the multiplier. Okay? The multiplier, this is simply equal to 1. Okay? So, if this is equal to 1, it will not affect the value. Okay? Because any number multiplied by 1 equals the same number. Okay, so this is equal to 1 also. Okay, so multiplying this, okay, you have to multiply here on d to the fourth and so as well small letter d to the fourth. Okay, so you have to distribute this doon po sa atin na nasa parenthesis po na yun. Okay, so simplifying this, we arrive at 16 td over pi quantity, we have there d to the 8th over d to the 4th minus small letter d, big letter d to the 4th over d to the 4th. Okay, so this is multiplied to the item inside the parentheses. Okay, and then let us then further simplify. What is common between these two is d to the 4th. So we have 16 td over pi d to the 4th.
So, ang left side
This is
copy,
common.
ang ating po right side fold method, distribute.
So, we'll have here, inilabas po natin yung d to the 4th. So, what is left here will be d to the 4th over d to the 4th minus small letter d
Then, copy
over d to the 4th. Laksan mo ng konti ang balas.
Inspection. I-arrange natin ang right side
Yan.
ng
Okay.
ang view.
Okay, so this one, okay, we can, okay, so we can have this
Then, by comparing, ang may x cube,
simplified, okay, so we come up now with 16t over pi d cube, okay, pi d cube, we have cancelled out yung d, okay, so leaving here d cube. So inside the parentheses, this is d to the 4th over d to the 4th, that is equal to 1 minus, this is small letter d over big letter d, and that is just the same as this k. Okay, that would be our diameter ratio, d over d. So this is equivalent to k, and then both are raised to the 4th, so that would be k to the 4th. Okay, so this is the simplified form, 16t over pi d cube times quantity 1 minus k to the 4th. Now, let us separate this 1 minus k to the 4th to this 1. Okay? So, we separate the two. Okay? So, to separate, we have 16t over pi t cube ay multiplied by 1 over 1 minus k to the 4th. Okay? And notice that this one, this is equivalent to your tau for the solid shaft. Okay? Diba? Tau for the solid shaft is 16t over pi d cube. Okay? We simply multiply it by 1 over 1 minus k to the 4th if it is hollow. So in that case, we call this now your hollow factor. Okay? So meaning tau for hollow, okay, is simply equal to tau for solid multiplied by 1 over 1 minus k to the 4th. Okay, so we call this your hollow factor. Okay, so that can aid you in ease of memorizing the equation. Okay, so tau for hollow equal to tau of solid multiplied by 1 over 1 minus k to the 4th. Again, k being your diameter ratio. Okay? And what we do sa design is then to equate the design stress to the induced stress of the material. Okay? So we'll have their tau D would be equal to tau for the hollow shaft. Okay? This would be equal to 16T over pi d cubed times 1 over 1 minus k to the fourth equal to your tau D. Okay? Where your tau D, this can be tau Y over factor of safety, or your tau D can be tau U over factor of safety dependent upon the basis of design. Okay? So it can be based on the yield or based on the ultimate. Okay? So you look at this equation now. Okay? So this would be simpler. Okay? If it is solid, you simply take this off. Okay? So alsin lang po ito. Okay? And then if it is hollow, you have to include the hollow factor. Since it's equal to the solid multiplied by the hollow factor. Okay? So ganun lang po siya kasi. Okay? So this is basically the same as that of our topic in the midterms. Okay? Design of machine members under pure torsion. Okay? Dito lang po, we introduce the diameter ratio. But whether you use the diameter ratio or not, it is just the same. So you can make use of this equation or yung atin pong equation na normal. Okay? Yung dati po natin ginagamit. Okay? Alin yung dati natin ginagamit? Okay? Yung 16T over this 2. Okay? So you can make use of this 2 or yung dinerive natin ngayon using the diameter ratio K. Okay? Any of the two will do. Okay? Just equate that to your design stress. Okay? Any question?
Okay, now.
Do you have a question?
Ang basic nating
Hello? Anyone?
is 1. For the first term,
Hello?
usap tayo.
Wala po, ma'am. Wala naman
Okay,
po.
so, okay, I'll proceed now. Let us have shaft under pure bending.
Ang iyo niya ay 2x dx. O dahil may x naman doon sa dx sa taas,
Okay, so this time it's shaft under pure bending. Okay, so how do you know that the shaft has a bending load? Okay, so how do you know that there would be a bending load? That is if you see a gear or a pulley loaded to it, just like this one. This is our shaft. Again, on the ends, these are the bearings. Okay, and then you have here, okay, loaded to the shaft is a gear or a pulley. Okay, so the gear or the pulley that serves as your bending load. Okay, so this serves as your bending load. Okay, so whenever you see a shaft loaded with this tool, okay, meaning there is bending. Okay, so the bearings on both ends that serves as your supports. Okay, and then from this, since it's bending, okay, we call our induced stress again as a flexural stress. Okay, so this is our induced stress, the flexural stress. And if you recall the flexural stress equation, MC over I. Again, M pertains to what? What is M? What is M, what is C, and what is I? Anyone? You raise your hand, please. How do you define M, C, and I?
Ay, ko daw yung 1 ha, sa record.
Negative 1
Pero kakasta lang.
Hello? Yes, Adriel.
Yung maximum moment po, ma'am.
Okay, correct. M pertains to the maximum moment, okay? C, that would be a perpendicular distance from the neutral axis to the outermost fiber. And I would be the moment of inertia, okay? But then unlike that, topics natin on midterm, that we have regular and irregular cross-sections, here we will focus only on a circular cross-section, okay? That is simply having a solid cross-section and a hollow one. Okay, so for a solid cross-section, let us recall that I for solid is simply pi d to the fourth divided by 64. Okay, whereas its C value, that would be diameter over 2. For hollow, I is equal to pi quantity d to the fourth minus d to the fourth divided by 64. And C is just the same, the outer radius, so d over 2. Okay, so with this, we can derive equation for the flexural stress. Say for example, for solid, okay, so for solid, flexural stress equal to M. And what is C for solid? That would be d over 2. And I would be pi d to the fourth divided by 64. Okay? So with this now, okay, you can cancel d. This will leave d cubed. 2 and 64, this will leave 32. So simplifying that, the flexural stress becomes 32m over pi d cubed. Okay? This is for a solid shaft. This is our flexural stress. Okay? So instead of using mc over I, you can go directly to this 32m over pi d cubed. Okay? And if it's hollow, what would be our equation? The flexural stress for a hollow shaft would be equal to 32m over pi d cubed. This is for solid. Just multiplied it by our hollow factor. Okay? And then from our previous discussion, what is the hollow factor? That is simply 1 over 1 minus k to the fourth. Okay? So that is simply the stress value. Stress value of the solid, okay, then multiplied by the hollow factor if it is hollow. Okay? And so this would be the flexural stress of a hollow shaft. Okay, solid multiplied by the hollow factor. Okay, and then again, what you will do is simply to equate. Okay, you equate the design stress to the induced stress of the material. So the design stress would be sigma d, since our induced stress is in form of sigma. Okay, so this is equal to the flexural stress equal to 32m over pi d cubed times 1 over 1 minus k to the fourth. So if it is solid, do not include this. Okay? If it is hollow, you have to include this part, the hollow factor, equal to your sigma d. Okay? Your design stress. Now, for the design stress, okay, how do you obtain the design stress? The design stress can either be sigma y over factor of safety, or, okay, your design stress can be sigma u over factor of safety. Okay? So, dependent again on the basis of design. Now, what is its difference from our previous discussion? Okay? M here pertains to the maximum moment. And how do you arrive at the maximum moment? Okay? If you have this, okay, you have to look for table 82. Okay? If you have the same setup as this one, you simply copy the equation for M maximum, and that's it. Okay? But then if not, okay, there is no other way but to create your shear and moment diagram to obtain the maximum moment. Okay? So just like this one. Okay? But then on our examples po, dati, okay, this bending load FB is already given. Okay? It is already given. But here on shaft design, this FB is unknown. Okay? So you have to know first the value of the bending load before you could arrive at the maximum moment. Okay? So how do you do that? Okay? How do you determine this bending load FB? This will not be given. Okay? So this will come from power. Okay? So shaft is of course used to transmit power. Two power equations are used. Okay? Alin niyo po yung pinakamalimit natin gamitin for equations ng power. We have listed there apat, okay, 4, but then we use only mostly 2 of these power formulas. Okay? What are those 2? Or can you please name one? One equation for power. Anyone? Okay, Jared.
Oy,
Ano po? P is equal to 2 pi T and all over 60 po.
Okay, correct. So power is equal to 2 pi Tn over 60. Okay, so we use this on the SI unit. Okay, and then another one,
Oh, ano daw?
Alex. Okay, yes, Alex.
P is equals to Tn over 63025 po.
Okay, so Tn over 63025. So we use this on the English unit. Okay, so from these two equations for power, okay, we can arrive at a value of the torque. Okay, so we can solve for the torque here. Okay, and from the torque, okay, you can solve now for the bending load FB. Okay, so you can solve for this FB. Okay, how? So you recall torque, okay, is equal to force times the radius. Okay,
Oh, James, Erwin.
okay, so force times the radius. So from there, FB would be equal to the torque divided by the radius of the gear or the radius or the pulley. Okay, so this is how you obtain your bending load FB, just like this one. Okay, so you should know the torque of the shaft. Okay, from there you can solve for FB, the bending load. Okay, and from the bending load, have now the maximum moment. Okay, using table 82, okay, on page 2, or you can create your shear and moment diagram, okay, to obtain M maximum, okay, to be used on our equations for the stresses. Okay, so that is how you obtain this bending load. Okay, FB. So that's the only difference from yung last po natin na discussion. Okay, because that is the value of the bending load is already given. Here on the shaft design, you have to determine this bending load. Okay, coming from the power transmitted. Okay, so what if your shaft contains multiple, okay, or multiple gears or pulley? Okay, say this is pulley 1 or gear 1, and then this one is gear 2. Okay, so you'll have here 2 bending load. So you call this FB1, and then the other one would be FB2. Okay, so same thing for our equation. Okay, your FB1 would be equal to torque over radius of gear 1, whatever the radius of your gear 1. And your FB2, okay, bending load would be equal to the torque over RG2. It should be the radius of this gear. Okay, for the value of the torque, okay, for the value of the torque, that will simply be equal. Okay, why is it equal? Because the two, okay, they are mounted on a single shaft. Okay, that is why the torque would be equal. So the bending load that varies only, okay, because of the radius of the gear. Okay, wala na pong iba. Okay, and then you have here on the bearings that will serve also as your supports. Okay, that is why you have your RA and you have their RC. That serves as the support, okay, of your shaft. So there are corresponding reactions on the support. So we call this RA, and this is equal to RC. So, in knowing the maximum and moment diagram, necessary that you know these values, okay, RA and RC. And that can be determined using, of course, equations of equilibrium. You can take moments on any of this side, okay, to obtain one unknown. Okay, so that is how we do it. Okay, so again, we design the shaft under pure bending, okay, using this equation, sigma equal to 32m over pi d cube times the hollow factor. If it is solid, you delete this. If it is hollow, then you have to include this. Okay? Question? Hello?
Factoring by group.
Again, so question now here is, how would I say that this is under pure bending where in fact, okay, you make use of yung torque, okay, from the power formula you solve for the torque, which has been the basis in knowing your
So, i-group mo o just sinabing ang
bending loads, okay, so that is used for the bending loads, okay. So what you need to do, okay, so what you need to do is simply, okay, solve for the bending load, okay, considering the power equation for the power and the torque, okay. And once you know already this bending load, you can create your own shear and moment line.
factor out ninyo ng x
Okay.
squared
Question?
x minus
Hello?
tapos yung the other group,
Wala naman po, ma'am.
ilabas mo ang
Okay,
negative 1.
so basically the same as that yung midterm po natin, okay. You have your sample problems, but then let us skip it first. I will go directly to the combined loadings. I'll give you time to answer the sample problems later.
Ang second group
Wait lang.
ay minus 1. At dahil po x squared minus 1.
Okay, shaft under combined bending and torsion, okay. So how do you know that it's combined bending and torsion?
Na dalawang linear na x plus 1 at isa pang x minus
Okay, so you have here the schematic diagram of the shaft.
Ang naging factor niya
You have the
ay
bearings on both ends.
dalawang x minus
You have here a,
at isa
say for example, a gear or a pulley, okay.
na
So that will give us the bending load. And then at the same time, this is rotating, producing torque, okay. So this is the schematic diagram of combined bending and torsion, okay. So how do we design combined loadings, okay? So for combined loadings, we have there two theories, okay. The first one, we call that the maximum shear stress theory.
o sino naman ang may awareness at na-discuss yung
And then the second one, we called it maximum normal.
Tampa po nakaka-experience ng synthetic fluid.
Okay, so these are the two theories. So ano po sinasabi on these theories? The first one, maximum shear stress theory, it reveals that, okay, when you combine, okay, bending and torsion, and then you subject a member to this kind of loadings, okay, so machine members tend to have more on twisting, okay, rather than on bending. So the dominating stress, okay, would be that of yung
Kung mga lesson na pang high school yun, algebra yun.
Okay, so, narinig pa po? Tumigil? Hello?
Magandang paraan.
Nag-connecting kasi. Meron? Narinig na, okay.
Yes po.
So, the maximum shear stress theory, okay, it says that failure will most likely occur, okay, on combined loads due to the twisting, okay. So, kumbaga, dominating stress is that torsional shear stress as compared to that of bending, okay. So, that is the maximum shear. So, for the equation, we use the symbol tau, and then we put there maximum. Kaya, maximum shear stress theory, okay. So, tau max would be equal to square root of tau squared, okay, plus sigma over 2 quantity squared, okay. So this is our general equation, okay, for your tau max. Okay, and under maximum normal, okay, symbol na gagamitin po natin would be sigma maximum, okay. And this is simply equal to what? Tau squared sigma over 2 plus tau square root of tau squared plus sigma over 2 quantity squared. Okay? So, this is the equation for your sigma max. Okay? So, to further simplify this is sigma over 2 plus tau squared plus sigma over 2 quantity squared. That would be equal to 1. Okay? Notice that this one is equal to your tau max. Okay? So, this part here is equal to your tau max. Okay? So, this would be the value for your sigma maximum. Okay? So, the two will be used, okay, whenever you have combined loadings. Okay? So, you use this in form of tau. Okay? And then, you can use also in terms of sigma. Okay? So, equation for tau max and sigma max. Okay? So, it's combination of tau and sigma. Okay? So, tau will represent torsion and sigma will represent the bending. Okay? So, from this, kindly derive, okay, equation for tau max and sigma max.
O ito, paano ka mag-long division sa cubic?
Okay, can you do it now? Okay, for the value of tau, okay, this will be for the torsion and sigma will be an equation for bending. Okay, so let us recall tau is equal to 16t over pi d cubed times the hollow factor. Okay, and for sigma, that would be 32m over pi d cubed times 1 over 1 minus k to d. Okay?
At dalawang negative 1. So, pipili ka doon. O pag napili mo ay
Okay, so this is what you will do now. Okay?
positive 1,
From the equation for tau max, okay, all tau would be replaced with this one. Okay, 16t over pi d cubed times the hollow factor. Okay, plus you have your sigma. Sigma is equal to this. Okay, so 32m over pi d cubed times 1 over 1 minus k cubed.
pwede ka na mag-long division or synthetic division.
Okay, so you do it now.
Ito
po, papalitan po natin.
Division by synthetic. Kung aralin ha, sa internet.
So, you replace this equation for torsion and bending in place of tau and sigma. Right? And then let us see what is your answer for tau max. Same thing with sigma max. Okay? So, you do it now.
At
Nagagawa niyo po ba? Hello?
repeated.
You try to derive.
So, ngayon, pag ating ginawa ang partial fraction, nalaman na natin ang case.
Okay, so let us try to derive here. Okay, so tau max.
So, by that,
is equal to tau square root of tau squared plus sigma over 2 quantity squared. Okay? Again, tau is torsion and sigma would be bending. Okay? So let us now substitute. For tau, that is 16t over pi d cube times 1 over 1 minus k to the fourth. And then this is raised to the second power. Okay? Plus sigma 32m over pi d cube, okay, times 1 over 1 minus k to the fourth. Divided by, okay, 2, and then you have to square this one, okay? So you try to simplify now. You look at the two terms and then see what is common between the two terms. What are those common? Miss Alisa.
Denominator. At ang C, multiply na lang siya
Hello?
yung denominator ng x plus 1.
Miss Alisa.
Okay, now.
Yung pi d cube
for
ko.
ABC, pwede ang
Again?
method 1, pwede ang method 2. Okay, ang ginawa po dito sa
Miss Alisa.
Pi d
video ay
cube ko.
method 2.
Pi d cube, okay? Pi d cube is common.
Then,
Same thing
combine
with
ang may x
16,
squared,
okay?
ang may
16
x at ang
over pi d cube. 16 is common since this is 32 over 2. So that is just the same as 16. So this is common, okay? Square root
Ang
of
constant ang x, c minus 2a,
16 over pi d cube squared. Okay? So squared kasi naka-squared pa po yan lahat. Okay? What else? Your
B is
Halo
negative a
factor 1 over 1 minus k to the fourth squared. This is also squared. So what is left here? Okay? So kung nilabas na po natin ito, ano po yung natira dito? So you'll have there only yes, t squared. Okay? So ito po nilabas natin, same thing with this one. So t squared na lang yung matitira. Plus, here, we have 32 over 2, that is also 60. Okay? So, dito naman po, we only have there m squared. Okay? So, these are extracted from this one. Okay? Being this factors common. Okay? So, these two, these are perfect squares. So, we can pwede po natin ilabas nung atin po na radical sign. Okay? So, these two, so, it becomes 16 over pi d cube, okay, times 1 over 1 minus k to the fourth, okay? And then, what is left here would be t squared plus m squared. So, this factor here, okay, this is equivalent to what we call TE, or the equivalent
unang equation.
twisting
so B is negative A. So, ang A ay 1 half.
Okay, so this is equivalent twisting moment. So therefore, you can finalize your answer. Your tau max becomes 16
plus 2
TE
times 1 half ay 1.
over pi d cube
equals
times 1 over 1 minus k to the fourth. Again, this TE, that's equivalent to square root of t squared plus m squared. Ito po yung nilagay natin kasama nung 16. And if you look at this equation, okay, this is somewhat similar to the pure torsion. Okay? Pure torsion simply is 16t over pi d cube. Since this is combined, instead of t, we make use of TE, which is the equivalent twisting moment. Square root of t squared plus m squared. Okay? So this is our tau max. And this tau max, the maximum shear, this is an induced stress. So what you need to do is to equate this to the design stress. Okay? So tau d would be equal to your tau max. Okay? Tau max is 16 TE over pi d cube if it is solid. If it is hollow, just multiplied by 1 over 1 minus k to the fourth equal to your tau d. And this tau d here, okay, this can be tau u over factor of safety, or this can be tau y divided by factor of safety. Okay, so any of the two. Okay, this maximum shear, okay, this is used if your member is a ductile material. Okay, so this is used only if the material is ductile and subjected to a combined torsion and bending. Okay, combined loads of torsion and bending yung shaft natin, and at the same time a ductile material. Okay, so you will be using the maximum shear stress theory, okay, to be equated to your tau d, which can be based on the ultimate or based on the yield. Again, your equation, it is similar to that of your torsion. Okay, so for ductile materials, failure under combined loading, okay, halos katulad po noong sa pure torsion. Okay, the failure is also only a twisting of the material rather than that of bending. Okay, they yield the same answer po, not the same derivation. Okay, we go now to the maximum normal. Okay, so maximum normal stress theory. Okay, for the equation, we yield here sigma over 2 plus tau maximum. Okay, so this is our equation. Okay, so this 2. So the maximum normal, this is good for brittle materials. Okay, so for brittle materials, if you have combined torsion and bending, okay, it would most likely fail doon po sa bending part, okay, not on the twisting. Okay, so that holds true on brittle materials. Okay, so from the equation, ganun po ulit ang gawin natin. Let us derive now equation for sigma maximum coming from this original equation or general equation. Okay, for sigma max, this is equal to sigma over 2 plus tau maximum. Okay, sigma pertains to the bending. Okay, so for bending, this is 32m over pi d cube divided by 2. This is times 1 over 1 minus k to the 4th. Okay, so this is sigma over 2 plus your tau max. What is our equation for tau max? Okay, your tau max is equal to this. Okay, so yun po ilagay natin, 16 TE over pi d cube times 1 over 1 minus k to the 4th. Okay, so you look at these two terms now. What is common? Just like when we simplify tau max. So what is common? Pi d cube, okay, over pi d cube. You have also here common is our hollow factor. Okay, and then this is 32 over 2. That is also 16. Okay, so those are the common ones. Okay, but then just like that of yung tau, okay, tau max, okay, let us have this sigma max synonymous with the equation for pure bending. Okay, so for pure bending, that's 32m over pi d cube. Okay, so yun din po ang gawin natin dito. Let us have here 32 over pi d cube, okay, times 1 over 1 minus k to the 4th. So these terms, okay, these are common to these two terms, okay. So these two factors, this is common to these two terms. So what is left here, okay, so 32 over pi d cube, this is the in-extract po natin, and so as this one. So what is missing is simply m over 2. So this is m over 2 plus, okay, here, okay, we extracted pi d cube. So ito po yun. This is the hollow factor, this is the hollow factor. So what is left is 16 TE. Okay, 16 TE. But then this is 32. Okay, to provide there 16, that would be TE divided by 2. Okay, diba? 32 over 2 will give us 16. Okay, kaya we have this now. Okay, to further simplify, this is 32 over pi d cube times hollow factor. Okay, This is equal to 1 half
Pwede pang i-divide
quantity
kasi x
m
squared dito,
plus
x,
TE.
4x squared dito.
Okay?
So, ang kailangan
This is
natin
1
sa
half
option ay 4.
m plus TE. Since common
Para
po
pag
yung
multiply
2
ninyo,
natin sa
parehas
ilalim.
ng 4x
Okay?
squared.
So, this now, okay, this
And
factor
4 times
here,
negative
1
1,
half of the
negative 4.
quantity
So,
m plus
itatapat sa
TE,
negative
this is
Then
equivalent
subtract.
ME. Okay?
Cancel na ang
You call
4x
that the
squared.
equivalent
Bring down yung
bending
walang katapat,
moment.
4x.
Okay?
Then
So we call this the equivalent bending moment. Okay? So with that now, okay, your equation
So our
becomes
result
sigma max
ating
equal to 32
remainder
ME
ay mababa na
over
ang power
pi
x na
d
lamang
cubed
ang ating
times
denominator x
hollow
squared. So tigil
factor.
na.
So if it is solid, alis
Pwede
po
na natin
are. Pag
isulat ng bago ang ating
hollow,
original na
isasama.
fraction
Okay?
na
So you look at our
ang
equation now
quotient.
for sigma max.
Susulat
Okay?
natin 3x
This
plus
is
4
the same as that
plus
of
remainder
pure torsion. Pure torsion is
4x
32 m
minus 2 o ang
over pi
remainder
d
lamang
cubed.
ang
Here we
lalagyan ng
use ME
denominator
since
na x
combined
squared
loading.
minus 1.
And what is ME? Simply
Okay.
equal to 1 half
Naintindihan po.
of the quantity m plus
Ito
t.
naman ba
Okay?
ay
So, this is again an induced stress. So equate this to the design stress. Sigma D equal to sigma max. 32 ME over pi d cubed times 1 over 1 minus k to the fourth equal to your sigma D. Okay? What is sigma D? Sigma D is simply equal to sigma U divided by factor of safety. You cannot use here sigma Y over Fs. Why? The maximum normal is valid for brittle materials. Okay? That is why we are using here sigma U over Fs. Okay? And for a brittle material, they do not have sigma Y. Okay? Kaya po ang ginamit dito is sigma U over Fs for the design stress. Okay? So, this sigma max and tau max, again, these are your induced stresses for combined loading, combined torsion, and bending. Okay?
1, 2, 3,
Question?
Miss Alessandra.
Wala po? Okay, so to provide a brief overview, okay, for torsion,
So, pag
what is
sinulat,
equation?
ang numerator
Tau
ay
equal
simpleng A
to
at bilang.
16t over pi
O, pwedeng
d
magpalit
cubed
ha.
times
Pwesto ang A at
hollow
B.
factor. Okay? For
O,
pure
tapos, get
bending,
the LCD. Copy the numerator. 4x
sigma
minus 2
equal
sa
to
left.
32
Sa right
m.
ay A
Sorry, this is
multiply sa
32.
hindi niya denominator, x minus 1. Plus B times hindi niya denominator, x plus 1. Then, pwede po ang method 1. Let x is positive 1. 4 minus 2 is 2.
8 lang.
0 na yung A na part. So, B, 1 plus 1 is 2. So, B is 2 over 2.
So sigma is 32 m
And the
over
other x
pi
that will make
d
it
cubed.
0
This
is
is flexural.
negative 1.
Times 1 over 1
So, 4 times
minus k
negative
to
1,
the
negative 4
fourth.
minus
Okay?
2, negative 6.
If it is combined.
Negative 1 minus 1, negative 2.
Pag combined, you have to pick whether it's
So,
tau
divide both
max
sides
or
by
sigma
negative 2,
max.
so
Okay?
A is positive
So
3.
tau max
So, therefore, the original
That would be
natin
16
ay pwede natin
TE
isulat sa dalawang
over
partial
pi
fraction,
d
3 over
cubed
x plus
times
1
1 over
x
1 minus k to the fourth, where
Which is now
TE is
easily
equal to
integrable.
square root of t
Pwede
squared
na po natin
plus
integral
m
ang
squared.
first term,
Okay?
parang ay nasa
Oh,
week.
so when are we to use this
At
tau
nasa
max?
midterm,
This is if
yung
it
bonus
is
point.
ductile.
Ano pa rin nagkamali?
Okay. If it is brittle,
the 3 power rule
you
is
use
straight over 2.
sigma max.
O, sino nakatama doon?
32 ME
So, 7.
over pi d cubed times 1 over 1 minus k to the fourth, where your ME is equal to 1 half of m plus t. Okay? So that would be the value of ME. This listed here, okay, listed here, these are all induced stresses, okay? So sa design, if you are to look for the dimension, then you have to equate this to the design stress. Tau D, you equate this to sigma D, okay? This one to be equated to tau D also. And then this one, sigma maximum, to be equated to your sigma. Okay? Any question?
Probably doon ang ating quiz.
None? Hello?
None so far po, ma'am.
Okay, so you may try solving for our sample problems, okay? So we have sample problem here, okay? Sample problem here is for a combined loading, okay? Then we go back to the first part, okay? Sample problems here, one is for pure torsion, and then two would be for pure bending, okay? This is for pure bending. So you try to answer these three sample problems again before we discuss the solution, okay? This is pure torsion, this is pure bending, and here, okay, this is combined torsion and bending, okay? So try solving it first.
Tamang simplest form. ano,
Naintindihan po yung gagawin for the sample problems. Nasa-solve nyo po before we could...
May mga bilang-bilang yan.
Yes po.
Sana ma-enjoy niyo yun.
Yes po.
Okay, good. So, sample problem 1, 2, and then the other one at the combined loadings. Okay? So, I would like you to see this first. Okay? For number 2, this one is under pure bending. But then you would say, there is a bending load here, FB. Okay? So, this is the bending load, FB, coming from the gear loaded to the shaft. Okay? But then, power transmitted here, okay, the power transmitted here, that will give us the torque, okay, wherein this torque will produce the torsional effect, okay, it will produce the torsional effect. So in that case, you would say that this is also combined, okay, since there is torque here coming from power and there is a bending load here from the gears attached to the shaft, then this is a combination of the two. Okay? But then with this statement, you consider bending effect only. Okay? So meaning the torsional effect is neglected. Okay? That is why we make use of the bending effect only. So this will fall under the pure bending. Okay? So the torque, okay, coming from the power will be used only to solve for the bending load FB. Okay? But then the torsional effect, the torsional shear stress will be neglected. Okay? But if you do not have this statement of considering the bending effect only, this will fall under, okay, combined loadings. Okay? So, yun po yung gagawin ninyo dito. So, you would have their bending effect only. And on the third one, okay, you have here given the torque already. Same thing with the moment. Okay? So, T and M. These are allowable shear stress and allowable tensile stress. So, the allowable shear stress, this is already your tau D. Okay? Allowable would mean the design stress already. Okay? Whereas this one, allowable tensile stress, this is your sigma D. Okay? So, the two are given already, tau D and sigma D. And this is simply mentioned as a shaft. No definite specification. No AISI, okay, name is given. So, it is a commercially available shaft, okay? So, how do you know if you will be using, okay, tau D or sigma D? Okay, so since you do not know whether this shaft is ductile or brittle, okay, so this is combined torsion and bending. And necessary, if the shaft is under combined torsion and bending, you should know first whether the shaft is ductile or brittle. From that, you could decide on what equation to be used. Will you be using tau max or sigma max? Okay, if it is ductile, you will be using tau max. If it is brittle, you will be using sigma max. But then in this case, in our sample problem, you do not know the type of material. Okay, so what you will do is you have to solve both. Okay, you need to solve tau max. Okay, you need to solve tau max, and at the same time, you need to solve sigma max. Okay, and then you have to equate this to tau D. This is to be equated to your sigma D. So therefore, two answers would be yield. Diameter coming from this maximum shear and diameter coming from the maximum normal. Okay, so there are two answers that you will yield. Okay, with these two answers, just choose the bigger one. Okay, and that would be your final answer. Okay, so again, we have to solve both since we do not know the type of material. Okay, nagkaintindihan ba tayo doon? Hello? Nakuha po ba yung gagawin dito for for the sample problem? Yes,
Yes po,
po.
ma'am.
Okay, so I'll leave that to you as your assignment, okay? And we will be discussing that on our face-to-face meeting tomorrow, okay? So I'll stop the presentation now. And then work on your own na po dito as your assignment. Okay, kung wala na po tayong question, you open first your camera for our attendance. Rio? Miss Rio?
Ako na lang po, ma'am.
Okay, thank you, Alex.
Pa-open na po ng cameras.
Ay, pareho ang background din.
Yan. Game na po. 1, 2, 3.
Okay, tapos na.
Isa pa po. 1, 2, 3.
Okay, thank you.
I'm done.
Okay na po. Thank you po.
Okay, thank you po. Bye.
Thank you po.
Everyone.
Salamat, mama.